Hello and welcome to this lesson for OCR A-Level Physics in the module of the Newtonian World and Astrophysics in the topic of oscillations and on the concept of simple harmonic oscillators. So if we've been successful and we've learnt in today's lesson, we should be able to describe the characteristics of simple harmonic motion, explain the conditions needed for simple harmonic motion, and calculate properties of simple harmonic oscillators. So in today's lesson, we're going to be looking at the following parts of the specification: 5.3.1 Simple Harmonic Oscillations. Now, objects can carry out oscillating motion based on Newton's laws of motion. So we can see on the screen now an example of oscillating motion. But what is the definition of oscillating motion? Well, oscillating motion is when an object moves either side of an equilibrium position in the same plane. Now, the equilibrium position will be the midpoint of the motion. The equilibrium position is the position in the motion where the object will reside under no force. The equilibrium position is the position in the motion where the object wishes to reside, because the equilibrium position is the position in the motion where the object is in its lowest potential energy state. Now, an oscillating object will always wish to return to equilibrium. So, as we know, oscillating objects do not stay at equilibrium because they have inertia in their motion. So oscillating motion is the motion back and forth about a fixed point in a straight line in the same plane. It is the repetitive motion along one plane of motion about an equilibrium position. Now, all oscillators share similar characteristics. In each case, the object starts in the equilibrium position, a force is then applied to the object, displacing it, and it begins to oscillate. So an example of oscillating motion can be a swing. An example of oscillating motion can be a rocking horse. An example of oscillating motion can be a clock. An example of oscillating motion can be Newton's cradle. An example of oscillating motion can be a pendulum. And an example of oscillating motion can be the chandeliers moving back and forth in Pisa Cathedral. Now, each of these systems is demonstrating simple harmonic motion, which is a special type of oscillating motion. Now, what is the difference between oscillating motion and simple harmonic motion, and what is so special about it? Well, simple harmonic motion is the special case of oscillating motion caused by a resulting force that repeatedly acts to restore a moving object to its equilibrium position. So, for example, a metronome, which is a doubly weighted pendulum, and a pendulum have simple harmonic motion because there is always a force acting towards the centre of oscillation. So, as we've said, simple harmonic motion is the oscillating motion produced by a force acting on the object to move it back to the equilibrium position of the motion, and this is called the restoring force. Now, the restoring force is always acting in the opposite direction to the movement as it wants to move back to the centre, so the force is negative. So what we would say is that the restoring force is directly proportional to the displacement from equilibrium. The further away from equilibrium, the larger the force. At equilibrium, there is no restoring force. Now, this also means that the greater the displacement from the equilibrium position, the greater the acceleration experienced by the object. So what we would say is that simple harmonic motion can be defined as an oscillation in which the acceleration of an object is directly proportional to its displacement from its equilibrium position and is directed towards the equilibrium. Now, this can be represented with the equation A is directly proportional to negative x. Now, if any equation contains this relationship, the object must be undergoing simple harmonic motion. Now, this is like an object carrying out circular motion. The centripetal force always acts towards the centre of rotation. Now, the centripetal force, literally meaning centre-secant force, is always acting towards the centre of the rotation. This therefore means that the centripetal acceleration acts towards the centre of rotation, the same direction as the centripetal force, because according to Newton's laws of motion, acceleration is always in the same direction as the resultant force that causes it. Now, it could be considered that the force and acceleration are trying to make an object move back to the equilibrium position of the motion, the centre. Now, we can consider an object carrying out simple harmonic motion, which is an object that's oscillating backwards and forth in the same plane. Now, in Newtonian mechanics, you can decide which direction is positive and which direction is negative. So it is up to you fundamentally in which way you're going to suggest it's going to be a positive motion and which way it's going to be a negative motion. Now we define in this motion that the equilibrium position as the midpoint in the oscillation. So the equilibrium position is the position where the pendulum would hang if there was no force placed upon it. The equilibrium position of an oscillator can be found by letting the object hang freely. Now the restoring force in simple harmonic motion always acts towards the equilibrium position. This is always acting in the opposite direction to the displacement, as shown in the following image. Now in circular motion, the resultant force always acts towards the centre of the rotation, and in simple harmonic motion, the resultant force always acts towards the centre of oscillation, the equilibrium position. So, the restoring force of simple harmonic motion is equivalent to the centripetal force of circular motion. So the restoring force of simple harmonic motion and the centripetal force of circular motion both wish for the object to reside in its lowest possible energy state. The restoring force does not keep an object an oscillating motion at equilibrium due to inertia, whilst the centripetal force does not keep an orbiting object at the centre of the rotation due to inertia. Now, this shows us that simple harmonic motion and circular motion obey the same laws of physics. The only difference is each motion has a different reference point for its centre of motion. And it shows us that simple harmonic motion and circular motion are both derived from Newton's laws of motion. They are the same physics principle from different frames of reference. So, if we displace an object in simple harmonic motion by a displacement of x, there'll be a force that will bring the object back to the equilibrium point. We call this the restoring force, and it always acts in the opposite direction to the displacement. We can represent this mathematically as this restoring force is proportional to the negative displacement. Now, as we know, F equals ma and the mass is constant in this system. Now this can also be written as therefore A is directly proportional to negative x. Now the minus sign implies that the restoring force and the acceleration acts in the opposite direction to displacement. So for example, if the object is displaced left, the restoring force and the acceleration act to the right. So F being proportional to negative x indicates that the restoring force is directly proportional to the displacement from equilibrium acting in the opposite direction. And A being proportional to negative x indicates the acceleration produced by the restoring force is directly proportional to the displacement from equilibrium acting in the opposite direction. Now either equation can be stated as the condition required for an oscillator to be acting as a simple harmonic oscillator. So, for an object to be moving with simple harmonic motion, its acceleration must satisfy two conditions. Firstly, the acceleration is proportional to the displacement. And secondly, the acceleration is in the opposite direction to the displacement, towards the equilibrium point. So we can consider the acceleration in simple harmonic motion to be a restoring acceleration, as it always wishes to bring an object back to the equilibrium position. We're now going to consider the equations of simple harmonic motion by looking at the motion of a simple harmonic oscillator. Now to fully analyse this motion, we must consider one cycle of a pendulum or any oscillating mass. In this example, we've defined left as negative displacement and right as positive displacement, but this is arbitrary. Now one cycle of the simple harmonic oscillator is the equivalent to one cycle of a wave or one rotation of circular motion. This indicates to us that the phase difference of one cycle is equal to 2 pi radians or 360 degrees. Now different oscillators can have different phase differences as shown in the following animation. Now oscillators can have a phase difference which is how much the oscillator will lag behind another oscillator. Now back to this definition of a cycle. We define one cycle as the pendulum bob being displaced in the negative direction at point 1. It is then released and swings through point 2 at its maximum speed until it reaches point 3 when it comes to a complete stop. It then swings to the negative direction, reaching a maximum speed at point 4. It then completes a full cycle when it stops at point 5. Now, at point 1, the pendulum has a maximum displacement in the negative direction. Now, as we said before, one cycle is the motion of the pendulum to return to its original position of maximum displacement. Point 2 is that the pendulum has a zero displacement from the equilibrium position. Point 3, the pendulum has maximum displacement in the positive direction. Point 4, the pendulum will have a zero displacement from equilibrium. And at point 5, the pendulum has a maximum displacement in the negative direction. Now this is one complete cycle for an oscillator. Now, if we consider the pendulum being displaced by a displacement of x as shown in the following image, amplitude A is the maximum possible displacement from equilibrium for that object. Now we think in this example the pendulum starts its motion at maximum displacement A, the amplitude. As the pendulum moves to the equilibrium position, its displacement is zero. When it moves to the maximum displacement in the opposite direction, it's negative A. Back to our equilibrium position, again its displacement is zero. Now at this point the body has inertia, so we'll keep moving past the equilibrium position. Then the pendulum will return to its original maximum displacement, the amplitude A. So we can summarise this information with the following diagram. Now, if we consider the displacement of a simple harmonic oscillator against time, we would get the following graph. Now we can express the x-axis of this graph as either time or angular displacement. Now because this is a cosine graph, it means that the cosine function must be present in the term to describe displacement. So what we would say is that the displacement of bob x after time t is given by the equation x is equal to a cos omega t, which is equal to a cos 2 pi ft. Now since f is equal to 1 over t, then this equation can become x is equal to a cos 2 pi 1 over t times by t, so therefore it equals a cos 2 pi small t over big T, where small t is the time into the cycle the oscillator is, and big T is the time taken for one complete cycle. This means that as the object displaces more and more, cos 2 pi t over t becomes closer to 1. Now this equation does use the small angle approximation, so we've got to use radians when we calculate values with cosine. Now this equation therefore is only true when the angle of displacement from the oscillator is 10 degrees or less. So this equation assumes that the object has started to oscillate from the maximum displacement position. If the oscillator starts oscillating from the equilibrium position, another form of the equation must be used, and that is x is equal to a sine omega t, or a sine 2 pi f times by t. This is because a cosine graph starts at a maximum, whilst the sine graph starts at zero. So to clarify, to work out the displacement when the oscillator started cycle at equilibrium, we would use x is equal to a sine omega t, whilst the displacement when starting from the maximum displacement is x is equal to a cos omega t. The correct equation to use is dependent on the starting conditions of the oscillation or the phase of the oscillation. So if the object begins oscillating from its equilibrium position, then at time is equal to t equals 0, the object is at its equilibrium position and its displacement is 0, so we must use the sine version. If the object begins oscillating from its amplitude, then at time t equals 0, the object is at its positive amplitude, so we've got to use the cosine version. So you can see this in the following graph shown here. For a mass on a spring oscillating from t equals 0 at equilibrium, and a mass on a spring starting oscillating at t equals 0 at maximum displacement. Now considering the displacement of a simple harmonic system shows the link with circular motion stated earlier in the following animation. Now we can calculate the phase difference between two oscillations in simple harmonic motion. The phase difference is the angular difference for the displacement between two successive oscillations, which is shown in the following animation. Now the phase difference between simple harmonic oscillators is equal to 2 pi small t over big T. Our unit of phase difference in this concept will be radians, and this only works when the oscillations have the same frequency or wavelength. The objects are coherent oscillators. Now the phase difference can be considered the difference in swing cycle between two pendulums. So the phase difference can be worked out by comparing the displacement time graphs of different simple harmonic oscillators, as shown in the following image on the screen. Now two identical pendulums oscillating in step both reach their maximum positive displacements at the same time. Their phase difference is 0 radians and they are in phase. If they are in anti-phase displacement, a phase difference of pi radians, one pendulum will be at its maximum positive displacement and the other pendulum will be at its maximum negative displacement. So if we go back again to considering our pendulum being displaced by x, we can now look at the velocity of the pendulum during this motion. When we start off at a displacement of negative x, the pendulum starts its motion at the maximum displacement a, its amplitude, and at this point the velocity is 0. This is because at this instance it's not moving. When we get to our displacement of equal to 0, the velocity is a maximum. Because as the pendulum moves through the equilibrium position, the velocity is at its maximum value. This is because there's no longer a restoring force on the object as it's in equilibrium. This means that due to F equals ma, there is no acceleration on the object. However, the object continues to move through equilibrium as it has inertia at this point. Then, when we've got a displacement of x, once again, the velocity is equal to 0, because at this instance, the object has stopped moving. Once again, we go back to equilibrium position, the displacement is 0, the velocity is a maximum, because there's no more restoring force or resultant force acting on our object at this point. But again, the object will continue to move through equilibrium as it has inertia at this point. The pendulum then returns to 0 velocity at its maximum displacement at the start of the cycle. So we can see here on our following diagram that when you have maximum displacement you have minimum velocity, and when you have minimum displacement you have maximum velocity. Now the velocity of the bob at displacement x is given by the equation v is equal to plus or minus 2 pi f or omega times by the square root of amplitude squared minus displacement squared. Now the plus or minus sign represents the oscillating motion of the pendulum. Now the maximum velocity occurs in the middle of the swing when we said that the displacement is 0, so x will equal 0. So as you can see here, we can work it through to get v is equal to plus or minus 2 pi f times by a. Now this is the maximum possible velocity for the object, and again the sign, the plus or the minus, depends on the way in which the object is moving in the cycle. Now if we consider again a pendulum displaced by x, we can now look at the acceleration of the pendulum during this motion. So again, if we have a displacement of negative x, the acceleration is at a maximum, because what we can say is that the resultant force and acceleration are proportional to the displacement. However, remember, the force and the acceleration act in the opposite direction to the displacement. When the pendulum bob hits equilibrium position, we know its displacement is 0 and its acceleration is also 0. Because as the pendulum moves through the equilibrium position, that will be the case, because as we said before, the resultant force and acceleration are proportional to the displacement. No displacement, no acceleration. When we get to our displacement of x, our acceleration is a maximum again, because we have a maximum displacement, because our resultant force and acceleration are proportional to the displacement. Once we go through our equilibrium position again, the displacement and acceleration will both be 0, because there's no displacement, so there's no acceleration. We then return back to our original position of minus x, and here we've got our maximum acceleration again, but remembering that the acceleration is in the opposite direction to the displacement. So we can summarize that when we have a maximum displacement, we have a maximum acceleration. When we have a minimum displacement, we have a minimum acceleration. The displacement and acceleration are always proportional to each other, but in opposite directions. Now this is indicated as one term has a positive value and the other term will have a negative value. The velocity of the oscillator is always the opposite compared to the displacement and the acceleration of the oscillator. So if you've got a maximum velocity, you'll have a minimum displacement and acceleration. Now, the acceleration of the bob at displacement of x is given by the following equation. Now always remember, the acceleration acts in the opposite direction to the displacement. So we can say a is equal to negative 2 pi f squared times by x, or a is equal to minus omega squared times by x. Now this indicates that this is simple harmonic motion. At these equations we can say a is proportional to negative x. So therefore, we can then say that the maximum acceleration occurs at the ends of the swing when the displacement is equal to the amplitude. So x is equal to a. That's because when the displacement is 0, the acceleration is also 0 because there's no restoring force. When the displacement is a maximum, the acceleration is a maximum because there is a maximum restoring force. So our maximum acceleration produced by the simple harmonic object is going to be a is equal to minus 2 pi f all squared times by a, or minus omega squared a. So, as I've said before, we know that a is equal to minus omega squared x. So this indicates that the proportionality constant between a and x must be considered to be omega squared. Now we can graph this as the following. Now, since the gradient for a particular oscillator has to be constant, this implies that the frequency and the period of the oscillator is also constant. Now, an important aspect of simple harmonic motion is that the period of the oscillator is independent of the amplitude of the oscillator. So as the amplitude increases, so does the average speed of the swing. So the period of the period does not change. Now, such an oscillator is referred to as an isochronous oscillator. So here we have a summary of the simple harmonic motion equations. That the general displacement equation is x is equal to a cos omega t or a sine omega t. The maximum displacement is x is equal to a. The general velocity is v equals plus or minus omega squared times by the square root of a squared minus x squared. On the maximum velocity is v is equal to plus or minus omega a. The restoring acceleration is a is equal to minus omega squared x in general, or for the maximum value, a is equal to minus omega squared a. Now remember, our restoring acceleration equations give us the condition of simple harmonic motion. The equation we can see up here is the equation used to work out the displacement from equilibrium at a particular time in the motion. This equation is used to work out the maximum possible displacement from equilibrium, the amplitude. This equation is used to work out the velocity at a particular time in the motion, whilst this equation is used to work out the velocity at the equilibrium position in the motion. And like we said here, these equations can work out the acceleration at any point in the motion, whilst this can work out the acceleration at maximum displacement. So to summarise what we've learnt in today's lesson, we've looked at displacement, amplitude, period, frequency, angular frequency and phase difference. Angular frequency is equal to 2 pi over t, which is equal to 2 pi f. Simple harmonic motion without defining an equation is a is equal to minus omega squared x. The solutions to the equations, including x is equal to a cos omega t or x is equal to a sine omega t, then velocity is equal to plus or minus omega times by the square root of a squared minus x squared, and the maximum velocity is equal to omega a. So if we've been successful and we've learnt in today's lesson, we should be able to describe the characteristics of simple harmonic motion, explain the conditions needed for simple harmonic motion, and calculate properties of simple harmonic oscillators. So thank you very much for watching this lesson on simple harmonic oscillators, which is part of the oscillations topic in the Module 5 Newtonian World and Astrophysics for OCR A-Level Physics. Thank you so much for listening and have a lovely day. Hello and welcome to this video on simple harmonic motion graphs, which is part of the topic Oscillations for Module 5, the Newtonian World and Astrophysics for OCR A-Level Physics. So if we've been successful and we've learnt in today's lesson, we should be able to use graphs to describe the characteristics of a simple harmonic oscillator, explain the conditions needed for simple harmonic motion, and calculate properties of simple harmonic oscillators. So we're going to be looking at the following parts of the OCR A-Level Physics specification, 5.3.1 Simple Harmonic Oscillations. Now the conditions for simple harmonic motion are the following. Firstly, the acceleration is proportional to the displacement, and secondly, the acceleration is in the opposite direction to the displacement, towards the equilibrium point. So this gives us an equation of a is equal to minus omega squared x. Now we can use these conditions to derive graphical interpretations of the oscillations which take place in simple harmonic motion. So let us consider the motion of the pendulum, a simple harmonic oscillator, in one cycle. So when released from point A, the bob accelerates and moves towards the centre point. Now the force and the acceleration are acting in the opposite direction to displacement, so we can say the displacement is a maximum. The force is a maximum, the acceleration is a maximum, but the velocity is zero. Now when it reaches point B, it has reached a maximum velocity in the positive direction and then starts to slow down. So this is the pendulum at its lowest point. It would rest here at equilibrium. So the pendulum is at what we call its equilibrium position. So its displacement is equal to 0. Its force is equal to 0. Its acceleration is equal to 0. And its velocity is at a maximum. Now at C, it has stopped completely, so its velocity is 0, and it's at a maximum displacement in the positive and accelerates in the negative direction. Once again, we know the force and the acceleration are acting in the opposite direction to the displacement. So the displacement is at a maximum, the force is at a maximum, the acceleration is at a maximum, and the velocity is at a 0. Back at D, it's at its centre point again, moving with a maximum velocity in the negative direction. So again, it's at its equilibrium position, with the displacement equal to 0, the force equal to 0, the acceleration equal to 0, and the velocity being a maximum. By E, the velocity again has dropped to 0, it's at its maximum negative displacement, and it has a massive acceleration as it changes direction. Once again, the force and acceleration are acting in opposite directions to the displacement. So our displacement is a maximum, our force is a maximum, our acceleration is a maximum, and our velocity is equal to 0. So if we assume the oscillator starts the cycle at a maximum displacement, we can graph the motion of this. So here our displacement time graph is a cosine curve. Now the amplitude of oscillations A can be found from the maximum value of x. The time period of oscillations t can be found from reading the time taken for one complete full cycle. In these particular graphs, we are assuming that no energy is transferred to the surroundings as the amplitude of each oscillation remains constant. Now the gradient of this graph leads us to the velocity of the oscillator. This allows the velocity time graph of the oscillator to be plotted. So we would get the following for our velocity time graph. The velocity time graph is the gradient of the displacement time graph, so a negative sine graph and 90 degrees out of phase with our displacement to time graph. As an oscillator moves fastest at its equilibrium position, therefore the velocity is at a maximum when the displacement is equal to 0. Now the gradient of this graph is the acceleration of the oscillator, so this allows the acceleration time graph of the oscillator to be plotted, and we would get the following graph. Now the acceleration graph is a reflection of the displacement graph on the x-axis. It's 90 degrees out of phase with the velocity time graph, and it's 180 degrees out of phase with the displacement time graph. Now this does indicate to us that the displacement and acceleration act in opposite directions, and this is shown in our simple harmonic motion condition. A is equal to minus omega squared x. So what this means is that when a mass has a positive displacement to the right, the acceleration is in the opposite direction to the left and vice versa. So the maximum value of the acceleration is when the oscillator is at its maximum displacement. Now this is shown because it's also the steepest part of the velocity time graph, and the gradient of the velocity time graph gives you your value of acceleration. Now if we assume the oscillator starts its cycle at the equilibrium position, the displacement time graph, the velocity time graph, and the acceleration time graphs will continue to be 90 degrees out of phase with the preceding graph. However, the pattern is now shifted by 90 degrees. So sine graphs have changed to cosine graphs and vice versa. Now, as we said before, we know that the displacement time graph will be a sine curve. The velocity time graph is the gradient of the displacement graph, so a cosine graph and 90 degrees out of phase with the displacement time graph. And the acceleration time graph is the gradient of the velocity time graph, so a negative sine graph and 90 degrees out of phase with the velocity time graph. So when oscillations start from the equilibrium position, we can see the following. So you can see our displacement time graph being a positive sine graph. We can see our velocity time graph going to be a cosine graph because it's 90 degrees out of phase with our displacement time graph. And then finally, our acceleration time graph is going to be a negative sine graph because it's 90 degrees out of phase with the velocity time graph, and it's actually 180 degrees out of phase with the displacement time graph. Now we can use the condition for acceleration to derive the restoring force in simple harmonic motion. The equation for acceleration, A is equal to minus omega squared x, can be substituted into Newton's second law, F equals ma. So this gives us a restoring force towards equilibrium of the following. F is equal to minus m omega squared x, which we can see on our following diagram here. This force is always acting to restore the oscillator back to equilibrium, and at the equilibrium position, therefore the restoring force will be zero. But our object will move past the equilibrium position in its oscillation as it will have inertia. Now at equilibrium position, the moving oscillator will continue to move at the same velocity past the equilibrium position. Now this indicates to us that simple harmonic motion is due to the combination of the restoring force acting on the oscillator and the inertia the oscillator has in it. So to summarise what we've looked at in today's lesson, we've looked at the graphical methods to relate the changes in displacement, velocity and acceleration during simple harmonic motion. And if we've been successful, and we've learnt in today's lesson, we are able to use graphs to describe the characteristics of simple harmonic motion, explain the conditions needed for simple harmonic motion, and calculate properties of simple harmonic oscillators. So thank you for watching this lesson on simple harmonic motion graphs, which is part of the oscillations topic in Module 5 Newtonian World and Astrophysics for OCR A-Level Physics. Thank you so much and have a lovely day. Hello and welcome to this lesson on simple harmonic motion energies, which is part of the oscillations topic in the module of Newtonian World and Astrophysics for OCR A-Level Physics. So if we've been successful and we've learnt in today's lesson, we should be able to detail the interchange between kinetic and potential energy during simple harmonic motion, calculate properties based on the energy stores of a simple harmonic oscillator, and understand and interpret energy displacement graphs for a simple harmonic oscillator. So we're going to be looking at the following parts of the OCR A-Level Physics specification. 5.3.2, the energy of a simple harmonic oscillator. Now in all simple harmonic motion systems there is a conversion between the kinetic energy store and the potential energy store. All undamped oscillators are considered closed or isolated systems where no energy is dissipated to the surroundings. Therefore, the total energy of a simple harmonic system remains constant. So we can say that the total energy is equal to the kinetic energy plus the potential energy, or that the total energy of the system is equal to the kinetic energy store of the oscillator plus the potential energy store of the oscillator. Now the total energy of a simple harmonic oscillator can also be referred to as the mechanical energy of the system. So as we said, in all simple harmonic motion systems, there is a conversion between the kinetic energy store and the potential energy store of the system. Now in this instance, the potential energy store is the energy due to the position of the oscillator in the gravitational field, whilst the kinetic energy store is the energy due to the oscillator moving. So if we consider a pendulum displaced by x, amplitude A being the maximum possible displacement from the equilibrium, at this point the pendulum is at its highest point, so the object will have its maximum gravitational potential energy store. So we can say the displacement is equal to A, the velocity we know is 0, and the acceleration is a maximum. Now if we continue to consider this pendulum undergoing simple harmonic motion, well, at the equilibrium position the object is moving at its fastest, so it's become a maximum kinetic energy store. So we know here that the displacement is 0, the velocity is a maximum, and the acceleration is 0. Now note, the restoring force does work on the object, allowing the energy to change store. If it then moves into our fallen position here, we know at this point the pendulum's at its highest point again, the object has become a maximum gravitational potential energy store again. So again, the displacement is minus A, the velocity is 0, and the acceleration is a maximum. Once again, back at its equilibrium position, the object is moving at its fastest, it's become a maximum kinetic energy store, the displacement is 0, the velocity is a maximum, the acceleration is 0, and then back again to end the cycle, it's at its highest point again, the object's become a maximum gravitational potential energy store with the displacement equal to A, the velocity to be 0, and the acceleration is a maximum. So we can summarise this as the following. You can see where you've got the maximum gravitational potential energy store at the maximum displacements and a minimum gravitational potential energy store at equilibrium. This is then opposed by the kinetic energy store, which is the minimum at the maximum displacement and maximum at equilibrium. Now remember, as it's a closed system, the total energy remains constant throughout the cycle. Now we can show this idea on a graph of energy against displacement. Now this is a graph for half a cycle of oscillation. Now note, displacement is a vector, so the graph has both positive and negative x values, but energy stores is only a scalar, so it can only be a positive value. Now here we can see how the energy stores of the oscillator changes with part of the cycle. Now for a simple pendulum, there's a transformation between the kinetic energy store and the gravitational potential energy store. At its lowest point, it has a minimum gravitational and maximum kinetic. At its highest point, where the displacement is a maximum, it has no kinetic but a maximum gravitational. So we can see here the points of minimum kinetic and maximum kinetic, and then on here the points of maximum gravitational potential and minimum gravitational potential. Now it is unlikely that an oscillator will ever have truly zero kinetic energy or gravitational potential energy in a cycle. Now the potential energy is represented by a parabola or a U-shaped curve, whilst the kinetic energy is represented by an inverse parabola or an N-shaped curve. Now we could also consider a mass spring system displaced. So a mass on a spring follows the same laws of physics as a pendulum, simple harmonic motion. Now here, as the mass spring has stopped moving, the kinetic energy is a minimum. Now there are two types of potential energy stores in this system, the gravitational and the elastic. So here, the elastic potential energy store is at a maximum, as is at its most stretched, and the gravitational potential energy store is at its minimum, as is at its lowest. Now we know here, the displacement is equal to a, the velocity is equal to 0, and the acceleration is a maximum. Now here we're at equilibrium and the mass spring is now moving at its fastest. The kinetic energy store is at a maximum. Once again, our elastic potential energy store is at a minimum as it's not stretched, and the gravitational potential energy store is still present as it's some way up. We know here the displacement is equal to 0, the velocity is a maximum, and the acceleration is 0. Now at this point, our mass spring has stopped moving, so the kinetic energy store is at a minimum. Now here, the elastic potential energy stores at a maximum, as at its most compressed or stretched, and the gravitational potential energy store is at a maximum, as is at its highest. So we know here, the displacement is equal to minus a, the velocity is 0, and the acceleration is a maximum. Now we come back to being at equilibrium again, where displacement is equal to 0, velocity is a maximum, and acceleration is 0. So here our mass spring is moving at its fastest, and the kinetic energy store is at a maximum. Again, the elastic potential energy store is at a minimum, as it's not stretched, and the gravitational potential energy is still present, as it's some way up. Again, here, at this part of our cycle, we know the displacement is equal to a, the velocity is 0, and the acceleration is a maximum. Again, here, the mass spring stopped moving, so the kinetic energy store is at a minimum. The elastic potential energy is at a maximum, as at its most stretched, and the gravitational potential store is at a minimum, as is at its lowest. So for a mass on a spring, there is still a transformation between a kinetic energy store, the gravitational potential energy store, and an elastic energy store. Now this graph combines the elastic and gravitational potential into one potential energy store. At the top, there's a maximum elastic potential energy store and the gravitational potential energy store, but a minimum kinetic energy store. At equilibrium, there's a maximum kinetic energy store, minimum elastic potential energy store, but there is still some gravitational potential energy store. Whilst at its lowest, it has no kinetic energy store, minimum gravitational potential energy store, but maximum elastic potential energy store. So this leads to a similar energy displacement graph as a simple pendulum. This shows that the energy displacement graph is consistent for one cycle of any simple harmonic oscillator. So once again, we have our points of maximum and minimum kinetic energy and maximum and minimum potential energy. Now for a simple pendulum, we can calculate the values of the different energy stores. We know that the gravitational potential energy store is equal to mgh, and the kinetic energy store is equal to a half mv squared. Now for a mass oscillating on a spring, we can calculate the values of the different energy stores. We know in this instance that our elastic potential energy store is equal to a half kx squared. Now the elastic potential energy is always positive and varies from when it's 0, when x is equal to 0, to a half k a squared where x is equal to a. Now the total energy of a system is when x equals a, because the object will be stationary for an instant. So this means that there's no kinetic energy. The total energy of the oscillator must therefore be equal to a half k a squared. Now the kinetic energy is equal to the total energy minus the potential energy, because the kinetic energy at any instant must be the difference between the total energy and the elastic potential energy. So we can say now our total energy is a half k a squared, our potential energy is a half k x squared, so we can write that as a half k open brackets a squared minus x squared. Now finally, the total energy of a system can also be written as the total energy is equal to a half times by the mass times by the angular velocity squared times by the amplitude times by the amplitude squared. Now we know that this comes from the substitutions on the simple harmonic motion equations of v and x into the equations. Potential energy is equal to a half kx squared and kinetic energy is equal to a half mv squared. So if we can summarize what we've learned in today's lesson, we can understand the interchange between the kinetic and the potential energy during simple harmonic motion when we understand the energy displacement graphs for a simple harmonic oscillator. So if we've been successful and we've learned in this lesson, we should be able to detail the interchange between kinetic energy and potential energy during simple harmonic motion, calculate properties based on the energy stores of a simple harmonic oscillator, and understand and interpret the energy displacement graphs for a simple harmonic oscillator. So that brings us to the end of this lesson on simple harmonic motion energies, which is part of the oscillations topic in OCR A-Level Physics, Module 5, the Newtonian World in Astrophysics. Thank you very much for listening and have a lovely day. Hello and welcome to this lesson for OCR A-Level Physics in Module 5, the Newtonian World and Astrophysics, in the topic of oscillations and looking at the concept of the simple harmonic oscillator systems. So if we've been successful and we've learned in today's lesson, we should be able to use the equations for simple harmonic motion in different systems, detail the techniques and procedures to determine the time period and frequency of simple harmonic oscillators, and then finally determining the time period and frequency of simple harmonic oscillators. So we are now going to apply our understanding of simple harmonic motion to two different systems, both of which have simple harmonic oscillators. These are the simple pendulum and the mass spring system. So if we consider a spring of natural length L0, which extends by a length x when a mass is suspended from it. When considering the tensile force on the spring, we can say F equals kx, where k is our spring constant or force constant, and this equation is Hooke's law. Now this can be written as T is equal to minus kx, which can then be substituted into Newton's laws of motion. Now we know Newton's second law states that A is equal to F over m, so then we can substitute in the Hooke's law equation into Newton's second law of motion and say A is equal to minus kx over m. Now in this instance k and m are constants, so this shows us that A is directly proportional to negative x. Now these are the conditions for simple harmonic motion, as simple harmonic motion occurs when the acceleration and the negative displacement are directly proportional. So if a mass on a vertical spring undergoes oscillation, it will have an acceleration given by A is equal to minus kx over m. But we're also aware that A is equal to minus omega squared x in simple harmonic motion. So we can equate the two terms and say minus kx over m equals minus omega squared x. So therefore, minus omega squared is equal to minus k over m, so omega is equal to the square root of k over m. Now we also know that omega is equal to 2 pi f, and we also can equate our two angular velocity equations to indicate to us that f is equal to 1 over t. So therefore we can then place the time period equation into the formula and get the square root k over m is equal to 2 pi over t. So therefore we can rearrange it and get our equation for the time period of one oscillation, which is t is equal to 2 pi times by the square root of m over k, which shows us how long it it takes for a mass spring to complete one whole cycle, and it also allows you to work out the spring constant of the spring, which is a second way of calculating this value from experimentation. Now please note the only factors in the time period equation are the mass and the spring constant. These are the only factors which affect the time period of an oscillating mass spring. No other factor is found in the equation, so this means no other factor can make a difference to the time period of one oscillation in this example of simple harmonic motion. So we can use the mass spring system equation to work out the spring constant of the spring in the system. Now to do this you must change the mass placed upon the spring and measure the time period of one oscillation of the spring. So if we say time period squared is placed against mass, we will get a straight line through the origin. Now we know t is equal to 2 pi times by the square root of m over k, or t squared is equal to 4 pi squared times by m over k. Now let's consider this as a straight line of best fit, so y equals mx plus c. So in this instance y is equal to t squared, x is equal to m, so therefore the gradient, or m in this case, is equal to 4 pi squared over k. So the gradient of the line of best fit of the graph is 4 pi squared over k. So our spring constant is 4 pi squared over the gradient. Now we can also plot the time period of one oscillation against the amplitude of the oscillation. Now here the time period squared is plotted against amplitude. Now this occurs because the amplitude of the oscillation does not affect the time period of the oscillation, as it's not found in the time period equation. So, the equation for the time period of a mass spring system is given by the following. T is equal to 2 pi times by the square root of m over k, where t is the time period of one oscillation of a mass spring in seconds. M is the mass of the system in kilograms, k is the spring constant of the spring in newtons per meter, and 2 pi are constants. Now the assumptions for this equation are that the spring is an elastic material and there is no dampening acting on the oscillator. Any factor not in this equation cannot affect the time period of oscillation for a mass spring system. Now you can change the mass of the mass spring in the investigation. You can measure the time period of one oscillation of a mass spring, and this allows you to derive the spring constant of the spring. Let's now have a look at the simple pendulum. To understand the mathematics of the simple pendulum, we must consider a pendulum bob of mass m on a light string of length L at an angle of theta to the vertical. Now this is considered a simple pendulum. There's a mass on a string of no mass, and there's a small displacement from equilibrium in the horizontal plane of motion. Now, we know there's a resultant restoring force acting towards the equilibrium position on the pendulum. This is the definition of simple harmonic motion. The restoring force always acts towards the equilibrium position. So we know our resultant restoring force is acting in the horizontal plane of motion, as this is the direction the pendulum is accelerating in. Now, the only force acting in the horizontal is the horizontal component of the weight. So this indicates to us the only force acting in the horizontal is the horizontal component of the weight, so it must be providing our resultant restoring force on the pendulum. So the resultant restoring force is the horizontal component of the weight, which is equal to minus mg sine theta. Now this has been found using the resolving components of the vectors found in the mechanics module we looked at previously. Now remember, the force must be a negative as it's acting in the opposite direction to the motion. We can then also use this to calculate the restoring acceleration, which comes from Newton's second law of motion, where F equals ma, so A is equal to F over m. So therefore A is equal to minus g sine theta. So what we know is F is equal to minus mg sine theta and A is equal to minus g sine theta. Now the acceleration is not exactly proportional to theta. However, if theta is less than 10 degrees, then sine theta equals theta when we're measuring in radians, so we can approximate this to A is equal to minus g theta. Now this idea is derived from the small angle approximation which we've encountered earlier in the module. Now this small angle approximation allows us to consider the displacement of equilibrium to be a straight line. Now also, this proves that motion must be simple harmonic motion, where A is proportional to minus displacement. Now we know that at small angles of displacement, 10 degrees or less, a pendulum is a simple harmonic oscillator. So in investigations, you can only displace a pendulum 10 degrees from equilibrium position and then gain accurate results. Now we can use these ideas to work out the time period of an oscillation for a simple harmonic pendulum. So consider a similar pendulum bob. The tension in the string is T and the displacement from equilibrium position is x. If theta is small, well, we know sine theta is x over L. This is because of small changes in displacement x, we can consider the displacement path to be a straight line and not a curve. So it allows us to use the rules of trigonometry, SOHCAHTOA. Now, we know that the pendulum undergoes oscillation with an acceleration given by A is equal to minus g sine theta, and we've also previously stated the relationship regarding the acceleration of a simple pendulum. It always acts towards the equilibrium position of the cycle. So we can then substitute in the values and say A is equal to minus gx over L. So we know A, as we said before, is minus omega squared x, so we sub that into the equation and we simplify it through to get omega is equal to the square root of g over L. We therefore also know that omega is equal to 2 pi over t, so we substitute that in, and we get t is equal to 2 pi times by the square root of L over g. So we know that from the previous idea, omega is equal to 2 pi over t. Now this gives us our equation for the time period of the pendulum. Now remember, we assume that if theta is less than 20 degrees, then it's accurate to within 1%. Generally, the assumption that a pendulum undergoing simple harmonic motion, which wants to use this equation, should only be made for displacements less than 10 degrees. Now, this also shows the only factors in the time period for a simple pendulum are the length of the string and the gravitational field strength. Nothing else affects the oscillation time period, not even pendulum mass or displacement from equilibrium. So our time period for a pendulum is t is equal to 2 pi times by the square root of L over g, where t is the time period for one oscillation of the pendulum, L is the length of the pendulum in meters, g is our gravitational field strength of the pendulum in newtons per kilogram, and 2 pi is constants. Now the assumptions for this equation are that the amplitude of oscillation is less than 20 degrees, the length of the pendulum is from the fixed position to the centre of mass of the bob, and there is no dampening acting on the oscillator. We term pendulums with these assumptions as simple pendulums. Now, any factor not in this equation cannot affect the time period of the oscillation of a simple pendulum. Now, you can change the length of a pendulum in an investigation. You can then measure the time period of one oscillation of a pendulum, and this then allows you to determine the gravitational field strength that the pendulum is in. So we can use the simple pendulum equation to work out the gravitational field strength the pendulum is in. Now, to do this, you must change the length of the simple pendulum and measure the time period of one oscillation of the pendulum, where t squared is proportional to L. Now, for a simple pendulum, we can say t is 2 pi times by the square root of L over g, or t squared is 4 pi squared times by L over g. So as we know, it's a straight line, so y equals mx plus c, y is t squared, x is L, and the gradient is 4 pi squared over g. So the gradient of the line at best fit of this graph is 4 pi squared over g. So the strength of gravity is 4 pi squared over the gradient. So we can also plot the time period of one oscillation against the amplitude of oscillation and have t squared against the amplitude. Now again, remember, the amplitude of oscillation does not affect the time period of oscillation, as it's not found in the time period equation. We could also plot the time period of one oscillation against the mass of the oscillator. Once again, the mass of the pendulum does not affect the time period of oscillation, as it's not found in the time period equation. This means one of the key investigations used to find the gravitational field strength has been to measure the oscillation time period of a simple pendulum. One of the first accurate measurements of the Earth's gravitational field strength was Qatar's pendulum in 1818. And in 1671, Richter worked out that the length of a pendulum with a swing of 1 second was 2.6 millimeters shorter in French Guiana than Paris. So this allowed us to show the Earth was not a perfect sphere with a uniform gravitational field. So this allowed Isaac Newton to work out this was due to the fact the Earth was not a perfect sphere, but slightly oblate. It was thicker at the equator because of the Earth's rotation. So we have used pendulum oscillation period measurements to determine the gravitational field strength. So measurements of a pendulum time period are currently used on the Earth to determine the geology of different regions. The first major example of this was the Geological Survey of India carried out in the late 19th century, and the Foucault pendulum in Paris was produced to derive the gravitational field strength on Earth, and it also shows how the Earth is rotating. Now, areas where the time period is shorter must have a denser rock material than the surrounding areas. Now in the future we could use pendulum oscillation time period measurements to determine the gravitational field strength on newly colonized exoplanets. A simple recording of the time period of a pendulum along with its string length would allow prospective colonists to determine the gravitational field of any astronomical body. Now for both simple pendulum oscillators and mass spring oscillators, you must consider how to reduce the errors and increase the accuracy of the measurements. So you'd measure the time for 10 or more complete oscillations and divide the number to get an average time period. This reduces the effect of the human reaction time on each individual oscillation. You should take at least 3 readings for each setup and calculate the mean to reduce random errors. Use a small amplitude, especially less than 15 degrees for pendulums, to ensure the motion remains simple harmonic. You would place a fiducial marker, a clearly visible reference point, at the equilibrium position of the oscillating object, and this helps you identify the midpoint of the motion accurately when timing and observing oscillations. Now, when observing the motion or reading measurements like extension or length, ensure your eye is level with the scale or fiducial marker. The parallax error occurs when the observer's eye is not directly in line with the measurement, leading to inaccurate readings. So fiducial markers help by providing a fixed visual reference. So you can see here how you can get an accurate value of measurement for either the simple pendulum oscillator or the mass spring oscillators. So to summarise, we've looked at the techniques and procedures used to determine the period or frequency of simple harmonic oscillations. Now, if we've been successful and we've learnt in today's lesson, we should be able to use equations for simple harmonic motion in different systems, detail the techniques and procedures to determine the time period and frequency of simple harmonic oscillators, and use the techniques and procedures to determine the time period and frequency of simple harmonic oscillators. So thank you for watching this lesson of the module Newtonian World and Astrophysics of OCR A-Level Physics, looking at the concept of oscillations and looking at the idea of simple harmonic oscillator systems. Thank you so much and have a lovely day. Hello and welcome to this lesson for OCR A-Level Physics, Module 5, the Newtonian World and Astrophysics, looking at the module of oscillations and the topic of dampening. So if we've been successful and we've learned in today's lesson, we should be able to define and describe a forced and freely oscillating system, describe and define a damped oscillating system, and detail the different types of dampening found on systems. So we're going to be looking at the following part of the OCR A-Level Physics specification, 5.3.3, dampening. Now, in previous lessons we've covered oscillations in several different oscillating systems. Now these include mass spring oscillators. So here you can see the mass spring moves in a periodic fashion. It exhibits simple harmonic motion. So an oscillating system with simple harmonic motion is one where the displacement of the oscillator is proportional to the acceleration of the oscillator in the opposite direction, or A is proportional to negative x. Now we can categorize all oscillating or vibrating systems into two different types. So there are two main types. The first one is free oscillators. Now these are oscillators which oscillate freely after being initially disturbed. So a swing is an example of a free oscillator. Now these systems are which ones that oscillate naturally. So these include systems that must be disturbed initially but then do not need a further force. So free oscillators only require an initial force. So if no external forces are applied to the system after it starts vibrating, it is a free oscillator. Now, free vibrations involve no transfer of energy into or out of the mechanical system. So in this system, no energy is transferred to the surroundings. System 2 is a forced oscillator. These are objects which have their oscillation produced when a driving force is placed on it. So a signal generator is an example of a forced oscillator. So a forced vibration is caused by a periodic driving force acting on the system. This periodic driving force causes work to be done into the system. So these are systems which always need a force to cause them to oscillate. These systems need to be driven constantly to cause them to oscillate back and forth. The force cause of this movement is called the driving force. So if a force is continually or repeatedly applied to keep the oscillation going, it is what we call a forced oscillator. So we know that there must be a periodic driving force. So consider a pendulum or mass spring system. They will oscillate after initial force is placed upon them. It does not need a constant force acting upon them to produce the movement after the initial force. If an oscillator is set into motion and has no periodic force acting on it, then it is described as a free oscillator. So a simple pendulum is an example of a free oscillator. It will continue to oscillate freely after it has been displaced. So once the initial force has been taken, the oscillator will still oscillate. Now a free oscillator produces free oscillations, defined as where a system is given an initial displacement and allowed to oscillate or vibrate freely. So a free oscillator system will oscillate at a set frequency called the natural frequency. So here we can see our pendulum vibrating at its natural frequency. The factors which affect the natural frequency are the terms in the equations used to calculate the time period of that oscillator. Now when an oscillator is oscillating as a free vibrator, there is ideally no energy put into or taken out of the oscillating system. So this assumes there is no dampening forces such as air resistance in the system. whilst the force oscillator has a periodic driving force acting on it, affecting its oscillation. This driving force is constantly acting on the system. So an example of a forced oscillator is a harmonic oscillator. They tend to have a motor driving the oscillation. So forced oscillators or vibrators can only be produced when a periodic driving force acts on the object. So the periodic driving force is placing energy or doing work into the oscillating system. So oscillators can be forced to behave in a different way to their natural motion. If, as a pendulum is swung one way, you were to push it in the opposite direction, it would turn back. So this action turns a free oscillator into a forced oscillator. This is a very energetic activity to do. It requires a lot of work to be done to achieve this. It is more efficient to allow a system to oscillate at its natural frequency. Repeated applications of forces from your hand in different directions can force a pendulum to oscillate at a different frequency. This would be a forced oscillation, and the frequency you were causing it to swing at would be the driving frequency. So forcing oscillating systems to not oscillate at its natural frequency involves adding energy to the system while it oscillates. If a system is not oscillating at its natural frequency, it is unlikely to undergo simple harmonic motion and will dissipate energy quickly. This is why a forced oscillator needs to maintain a constant driving force to maintain its frequency. It's much easier to let an oscillating system oscillate at its natural frequency than drive it. Now, many oscillating systems, such as piano strings, can be forced to oscillate, but oscillate best at their natural frequency. The driving force puts energy into the system at a certain frequency, not necessarily the same as the natural frequency of the system. The natural frequency is the frequency in which a system would oscillate if there was no driving or dampening force. Now, many oscillating objects, such as yo-yos, can be forced to oscillate, but oscillate best at their natural frequency. If a yo-yo is allowed to hang freely and move up and down naturally, it's carrying out a free vibration. It's vibrating at its natural frequency. If a yo-yo is made to vibrate by a periodic driving force of moving your finger up and down, the yo-yo is carrying out a forced vibration. The frequency of the oscillation is the driving frequency. If the driving frequency produces a driving force produces a driving frequency, which is the same as the natural frequency, then the amplitude of the oscillation is at its largest. So, free oscillations involve no transfer of energy to or from the surroundings. These are natural oscillations once a system has been displaced from equilibrium, and the system oscillates at its natural frequency. Forced oscillations involve energy transfers into the system from a periodic driver, oscillations in a system due to a periodic driving force, and the system oscillates at its driven frequency. So an object which is freely oscillating is observed to dissipate energy to the internal energy of the surroundings. So if a system is performing simple harmonic motion at its natural frequency, it will dissipate energy through a friction force on the system. So in this example, friction causes energy in the simple harmonic system to transfer to the internal energy of the surroundings, and air resistance causes energy in the simple harmonic system to transfer to the energy to the internal energy of the surroundings. Now, if a pendulum is left to swing without interference, its amplitude will decrease with each swing owing to its air resistance and internal stresses due to the flexing of the material of the string. Now, although the amplitude decreases, the period for one oscillation remains constant throughout. The forces which reduce the motion of the oscillator and dissipate energy are called dampening forces. These frictional forces oppose the motion of the oscillating body. They slow or simply stop simple harmonic motion from occurring. So the effect of an oscillating system decreases in amplitude due to losing energy from the simple harmonic motion system to the surroundings, and that is called dampening. So dampening forces are resultant forces which cause work to be done from an oscillating system to the surroundings. Now, we know that another name for dampening forces is dissipative forces. Now, this is because the dampening forces dissipate energy into the surroundings. Now, energy is transferred from the mechanical system to the internal energy of the surroundings. These forces make our system an open system. Now, systems are often deliberately damped to stop them oscillating or to minimize the effect of resonance. Now, parts of systems which are designed to produce dampening forces are called dampeners. So here are some examples of car dampeners found on the wheels of cars. Now, the dampening types are classified by the effect that they have on the oscillating motion of the system. Now, the amount of dampening can vary, and this can determine its effect on the vibration of the system. There are 4 different types of dampening. The first type is underdampening or light dampening. This is dampening that slowly reduces the amplitude of the oscillations but keeps the time period and frequency almost constant. So in this type of dampening, the oscillator continues to oscillate back and forth, the amplitude decreases each time, but the frequency stays the same. In real terms, the oscillator decreases in swinging over time. Most types of oscillators in the real world have light dampening. Now, we know that basically, in real terms, the oscillator decreases in swinging over time. So we can say that the dampening effect here is very gradual, that the amount of the amplitude changes each time is very small. So we can see that straight away. Now, many systems are underdamped and oscillate whilst their amplitude decreases exponentially, such as the mass oscillating on a spring. So the dampening might be quite small, but eventually the mass comes to rest. Now, examples of light dampening include the simple pendulum and the mass spring system. The second type is heavy dampening. This is dampening that reduces the amplitude of oscillations but keeps the time period and frequency almost constant. In this type of dampening, the oscillator continues to oscillate back and forth and the amplitude decreases each time, but the frequency stays the same. In real terms, the oscillator decreases in swinging over time. Now here, the dampening effect is quite fast. Heavy dampening is the same as light dampening, except it takes less time to stop oscillating. So it is the same as light dampening, except the reduction in amplitude is greater. Now, examples of heavy dampening include the simple pendulum and the mass spring system. However, the resistive forces will be increased by using objects with larger surface areas, as this would increase their air resistance. The third type is called critical dampening or very heavy dampening. This is when an oscillator returns to its equilibrium position in the quickest possible time without going past the equilibrium position. So in this type of dampening, the oscillator returns to equilibrium without making one oscillation over as quickly as possible. So in real terms, the oscillator returns to the center after being displaced very quickly. So a critically damped oscillator returns to equilibrium position very quickly. The dampening effect here is very sudden. So a critically damped oscillator returns to equilibrium position very quickly. An example of a critically damped system is the shock absorbers in a car. It's advantageous to have the oscillations decay as fast as possible. So here the system does not oscillate but asymptotically approaches the equilibrium condition as quickly as possible. So for critical dampening, the graph has a fast decreasing gradient when the oscillator is first displaced until it reaches the x-axis. Now finally, we have overdampening. This is when an oscillator returns to its equilibrium position in a very slow time, without going past that position. So in this type of dampening, the oscillator returns to equilibrium without making one oscillation over a long time period. In real terms, the oscillator returns to the center after being displaced very slowly. So a heavily damped oscillator returns to the equilibrium position very slowly. The dampening effect here is very gradual, and it's the most dissipative dampening effect. So overdampening can be considered to be extreme critical dampening. So for overdampening, the graph has a slowly decreasing gradient from when the oscillator is first displaced until it reaches the x-axis. So we can summarize dampening as the following. There are 4 types of dampening. Underdampening or light dampening. Dampening that slowly reduces the amplitude of oscillations but keeps the time period and frequency almost constant. Heavy dampening. Dampening that reduces the amplitude of oscillations but keeps the time period and frequency almost constant. Critical dampening, when the oscillator returns to its equilibrium position in the quickest possible time without going past that equilibrium position. And finally, overdampening, when the oscillator returns to its equilibrium position in a very slow time without it going past that position. Now, all types of dampening reduce the amplitude of oscillation over time. Generally, the heavier the dampening, the quicker the amplitude is reduced to zero. An exception to this is overdampening. All types of dampening dissipate energy from the mechanical system to the internal energy store of the surroundings. So it's a very important key idea. Now, in the case of damped motion, the kinetic energy of the oscillator is transferred to other forms, usually heat. Now, critical dampening is often desired because such a system returns to equilibrium rapidly and remains at equilibrium as well. In addition, a constant force is applied to a critically damped system and it moves the system to a new equilibrium position in the shortest time possible without overshooting or oscillating about the new position. Now, plastic deformation of ductile materials reduces the amplitude of oscillations in periodic motion in the same way as dampening. As the material changes shape, it absorbs energy, so the oscillation becomes smaller. So that brings an end to our lesson today. Let us summarise what we've looked at. Free enforced oscillations, the effects of dampening on an oscillating system, and observed forced and damped oscillations for a range of systems. So if we've been successful and we've learned in today's lesson, we should be able to define and describe a forced and freely oscillating system, define and describe a damped oscillating system, and detail the different types of dampening found in systems. So thank you for watching this lesson on dampening, which is part of the oscillations topic in OCR A-Level Physics Module 5, the Newtonian World and Astrophysics. Thank you so much and have a lovely day. Hello and welcome to this lesson for OCR A-Level Physics, looking at the Module 5 of Newtonian World and Astrophysics in the topic of oscillations and looking at the concept of resonance. So if we've been successful and we've learned in today's lesson, we should be able to define what resonance is, look at the effect of resonance in different applications, and detail the effect of dampening on resonance. So in this lesson, we're going to look at the following parts of the OCR A-Level Physics specification, 5.3.3, dampening. Now, when a system acts as a free oscillator, it oscillates with a natural frequency f0. If that system, when it's acting as a forced oscillator, has a driving frequency the same as the natural frequency, then the amplitude of oscillation becomes very large. This is called resonance. So the graph shows here the amplitude with which a simple harmonic oscillator will oscillate against the driving frequency applied to it. Now, resonance can only act on a forced oscillator. So resonance only occurs when the driving frequency equals the natural frequency. Now, resonance can be observed with a massive increase in the amplitude of an oscillating system, and resonance leads to a large increase of energy into the system. So here's a graphical version of resonance. Now here's a simplified version of the resonance graph. Now we can identify the resonance frequency of a system from identifying the frequency with the highest amplitude. So you can see here A and C are at low amplitude while B is at a high amplitude. Or we could say that A and C are at a low energy store whilst B is acting as a high energy store. So where B is our resonant frequency, which is also the natural frequency of the system. Now, to determine the resonant or natural frequency of the system, you must take many experimental points around the peak of the graph. Now, this could also be described as decreasing the interval around the peak values of the graph to determine our resonant frequency accurately. So for any oscillator, as we mentioned before, the effect of resonance happens when the natural frequency equals the driving frequency. Now this means the system can absorb energy from the driving force easily, and this increases the amplitude. Now pushing a person in a swing is a common example of resonance. The loaded swing, which is a pendulum, has a natural frequency of oscillation, and when the driving frequency is equal to this, resonance occurs and the swing goes a lot higher. Now, resonance can only be observed in forced vibrations, as the driving force is where the oscillator absorbs the energy from. Now, dampening makes the simple harmonic energy in the system move into the internal energy of the surroundings. This means that dampening lessens the effect of resonance. So dampening will reduce the size of oscillations at resonance. There's still a maximum amplitude reached, but it's much lower than when the system is undamped. We can also say that dampening reduces the sharpness of resonance. So the dampener makes the simple harmonic energy in the system move to the internal energy of the surroundings. The dampening would lessen the effect of resonance, so the stronger the dampening, the smaller the effect of resonance. So if you want to lessen the effect of resonance on your system, either change the natural frequency of the material or include dampeners. Now, dampeners reduces the sharpness of the resonance. This means the dampener lessens the effect of the resonance spike in the amplitude. Heavily damped systems have a flatter response to an increase in driven frequency. So this is what we said as heavily damped systems are not as sensitive to the driving frequency. Heavily damped systems have a resonant frequency slightly lower than the natural frequency. So heavily damped systems shift their peak further to the left-hand side of the graph. Now, dampening causes energy stored in the system due to resonance to be dissipated to the internal energy store of the surroundings. So the lighter the dampening, the larger the maximum amplitude becomes at resonance. The closer the resonance frequency is to the natural frequency of the system. And when the dampening is lighter, the resonance curve is much sharper. But the heavier the dampening, the smaller the maximum amplitude becomes at resonance. The greater the gap between the resonant frequency and the natural frequency. and the resonance curve is much duller or flatter. Now, every oscillator system can undergo resonance. We observe this effect in many everyday situations, and this can be shown in our following situation. Here, the balls which move the most must be undergoing resonance, as it has the greatest energy store and then the greatest amplitude of oscillation. So to undergo resonance, the natural frequency of the pole must equal the driving frequency of the man. Now consider a washing machine. The motor of the machine drives the vibrations in the machine which are at its natural frequency of one of the washing machine panels. A washing machine is very noisy during one part of the cycle. Here the motor is spinning at a certain frequency. So we can say that at some point of the washing machine cycle, the driving frequency of the motor equals the natural frequency of the metal. This causes the panel to vibrate with increasing amplitude, making a loud noise, and may even cause the machine to move. During the rest of the wash cycle, the motor rotates at frequencies which do not match the natural frequency of any part of the machine, and it's much quieter. A system can be made to oscillate with the driving force. So when the driving force begins to oscillate, the driven object has a phase difference between the driving oscillation and the oscillating object, which is zero. So what we can say is that the driver and the driven are in phase. So at the start of the process, the signal generator, which is the driving oscillator, and the spring, the oscillating object, are in phase. However, if the system or object is forced to have its driving frequency at its natural frequency, it will absorb more and more energy, which increases the amplitudes of oscillations. And this is resonance. So when resonance is achieved, the phase difference between the driving oscillation and the oscillating object is pi/2 radians. So when the spring resonates, the signal generator is pi/2 radians, or 1/4 of a wave, ahead of the spring. The signal generator is leading the spring into oscillating, so the signal generator is providing the energy into the oscillating system. Now, if a system or object is forced to have its driving frequency at its natural frequency, like we said before, it will absorb more and more energy, which is where we have our actual resonance. So what we know is that before resonance, the phase difference between the driver and the driven is 0 pi radians, so the driver and driven are oscillating with the same cycles. At resonance, our phase difference between the driver and driven is pi/2 radians, so the driver is 1/4 of a cycle ahead of the driven. Whilst after resonance, the phase difference between the driver and the driven is pi radians, so the driver is half a cycle ahead of the driven. So we can summarize the properties of the force vibrations as follows. When we apply a frequency to the driven oscillator, when the driven frequency is below the natural frequency, the amplitude increases as the frequency increases. When the driven frequency is the same as the natural frequency, the amplitude is at a maximum. Now when the driven frequency is above the natural frequency, the amplitude decreases as the frequency increases. When the driven frequency is below the natural frequency, the phase difference starts at 0 and increases as the frequency increases. When the driven frequency is the same as the natural frequency, the phase difference between the two is half pi. Whilst when the driven frequency is above the natural frequency, the phase difference starts at a half pi and then increases to pi as the frequency increases. Now a simple setup of several pendulums can demonstrate resonance. A heavy swinging ball acts through a suspension wire to drive all the other pendulums at its natural frequency. Only the pendulums with the same natural frequency vibrate with a large amplitude, as this is the pendulum that resonates. This pendulum has the same length of wire as the driving pendulum. The other pendulums show little movement because the driving frequency does not match their natural frequency. Now this setup is called Barton's pendulum. So here's a picture of Barton's pendulum. Pendulum X acts as the driving frequency of the pendulum. As this is the driving force at resonance, it's oscillating pi/2 radians ahead of the pendulum it makes oscillate. Only the pendulum with the same string length will have the same natural frequency as the driving frequency. So this means that the pendulum with the same string length as the driving pendulum will vibrate with its resonant frequency. Now this will be observed with the pendulum oscillating at a higher amplitude than the other pendula. So here's a picture of Barton's pendulum. We have our driving pendulum, which provides the driving force to move the other pendula. And here are our driven pendula. The different driven pendula are moved by the driving pendulum. Now, in this example, pendulum B will oscillate in resonance as it has the same natural frequency as the driven frequency. This is because it has the same frequency as the driving pendulum, as they have the same length, which is what affects the frequency and time period of the pendulum. Now, the driving pendulum will oscillate pi/2 radians ahead of pendulum B, as when it drives it, it leads the pendulum by giving it energy. So to summarise in this lesson, we've looked at what resonance and natural frequency is. So if we've been successful and we've learned in today's lesson, we should be able to define what resonance is, look at the effect of resonance in different applications, and detail the effect of dampening on resonance. So thank you so much for watching this lesson, which is part of Module 5 in OCR A-Level Physics, the Newtonian World and Astrophysics, looking at the topic of oscillations and the concept of resonance. Thank you so much for watching, and have a lovely day.